Hello there, lovely ones. So we are looking at how to sketch cubic functions, and I've taken these questions from the Mind Action Series 2019 version, and it's grade 12, chapter 4, exercise 7, and page 111. Okay, so when you are asked to sketch any kind of function, you're going to need to find out a couple of pieces of information, regardless of what the function is. Firstly, you need to get an idea of what the shape is. Is it a parabola, hyperbola, cubic function, etc.? You also need to figure out your x-intercepts and your y-intercepts, and those by now hopefully you're very fluent in doing. But now, because it is a cubic function, you're going to figure out your stationary points and your point of inflection as well. So you're going to get marks for knowing what each one of these are. So a question where you're plotting a cubic function can actually be worth quite a lot of marks. Something I just want to remind you of, a stationary point, that's the point where the function is both increasing and decreasing, and as a result it is, well, it's a turning point. It looks like it's standing still. Okay, so let's start by determining the shape of it. So because a is more than 0, in other words it's positive over there, we know that our cubic function is going to end off by going up. So there we go. That's the shape. The y-intercept I'm going to do next because it's, well, it's easiest. And we do that by substituting 0 in for x, and of course, you can just see the answer. You don't have to do all of these calculations. You know that it's going to be 0, and let's write down the coordinate. So far that's 2 marks. The x-intercept, to find the x-intercept, we've got to make y equal to 0 and then solve for x. Now you can use the factor and remainder theorem to do this if you're struggling to factorize and stuff like that, but in this case it is actually quite doable to factorize, and I'm doing that by taking out a common factor of x squared. So that means x is either going to be equal to 0 or it is equals to 3. Our x-intercepts therefore are going to be 0 and 0 and 3 and 0. And that kind of makes sense, or it does make sense, because our y-intercept is at 0 and 0, so it must be true that our x-intercept is also there. Stationary points and points of inflection. This is where we use our first derivative and our second derivative. So I'm going to find the first derivative first, 3x squared minus 3x. Sorry, that's actually minus 6x. Let's make that correction. And then while I'm at it, I'm just quickly going to write down what the second derivative is. Just to save time, it's going to be 6x and minus 6. Okay, so to find the stationary points, we need to make the first derivative equal to 0, and then we can factorize it to find the value of x, and this actually turns out to be quite simple because we're taking out a common factor of 3, and it leaves us with this. So therefore, our stationary points are where x is equals to 0, and x is equals to 2. Now, before I go and I waste everyone's time, I've already calculated where x is equals to 0. So, and I've done it actually 3 times, or twice. It would be 3 times if I'd done this as well. So I'm not going to do that. I'm just going to acknowledge the fact that the one stationary point does happen at that point. The other stationary point, I've got to substitute the value of x back into the original function. So that's going to be 2 to the power of 3 minus 3, and it's 2 to the power of 2. When I put this into my calculator, I get an answer of -4, and please remember to use your calculators. Always, always use them. Okay, then lastly, we need to find the point of inflection. But before we do that, I'm just going to do a rough sketch quickly of the information we have. We know that it's going to 0, 0. We also know that 0, 0 is one of the turning points, which means that it's going to look like that. The other turning point is here, roughly 2 and -4. And then this was our x-intercept, which was 3 and 0. And so our point of inflection, we're expecting to lie somewhere over there. Okay, but let's go on to the point of inflection. We find that by making the second derivative equal to 0, and then we solve for x, which of course is going to be 1. That's just the x-coordinate. We then have to substitute it back into the original equation. And remember that you should be using a calculator to do this. And of course, we're going to get an answer of -2, making our point of inflection 1 and -2. So that point over there is going to be 1 and -2. So now the job comes in where you've got to plot the function. you're going to use a ruler to make the axes, and you're going to kind of judge where they should be, and then your points need to be in proportion to each other. So if you put 0, 0 there, and 3 and 0 here, you can't have 2 and negative 4 there because it doesn't make sense. It's got to be more down there. And you would do it as neatly as you can. One of the tips I can give you is don't try and draw the line all in one. Rather draw little bits at a time, and then it's easier to make the curves. And here I have plotted it as neatly as I can, and you'll see that 0, 0 is marked, and so is 1 and negative 2, and 3 and 0, and then the 2 and negative 4. In order to get full marks, you must have marked where those points are. It shows us that you understand what the meaning of each point is. So we're going to run through question B a little faster from the same exercise. Once again, we're looking at all of these different pieces of information we need. The shape, it's a cubic function, it's going to go down because we're not adding anything, we're adding 0. Our y-intercept we know is going to be 0, 0. For our x-intercept, we've got to make y 0. Lots of zeros being said here. But anyway, we make y 0 and then we solve for x by using factor theorem or by factorizing. The stationary points we're going to find by finding the first derivative first, which is negative 3x squared plus 12x minus 9, and then we'll make that equal to 0, so negative 3x squared plus 12x minus 9. And then lastly, the point of inflection is going to be the second derivative, and we'll make that equal to 0, but first let's write down what it is. It's going to be negative 6x plus 12. So why don't you give it a go, calculate all of those. I started by finding the x-intercept, and you'll see that I took out a common factor of negative x first, so that I had an easier to solve trinomial. Once I did that, I found that x would be 0 and that x would be 3. So I factorized to find the stationary points, and I would then substitute those values back into the original function. And I'll tell you why I'm being silly just now. Plus 9, and it's 3. And the reason I was being silly is because I already know that where x equals 3, the coordinate is going to be 0 and 3. So you don't have to show those calculations. If you know the answer immediately because you've calculated it already, you don't have to. Functional notation is actually really useful because it reminds you what you're substituting into where. So I've said that I'm substituting the value of 1 in for x in the original function. So squared minus 9 and the value of 1, and of course that is going to give me an answer of negative 4. So our other stationary point is going to be 1 and negative 4. So now I've solved for the x value of the point of inflection by making the second derivative equal to 0. After that, I've only got the x coordinate. I still need to discover what the y coordinate is. And the way I do that is by substituting it back into the original function. And guess what? You do have a calculator. You should very, very definitely be using it to do this. So that coordinate is going to be 2 and negative 2. So to do a very, very rough sketch of what's happened so far, I've got a y-intercept of 0, 0. It's also my x-intercept. Got an x-intercept of 3 and 0, so that's 3, that's at 0. Our stationary points, one of them is going to be over there, and the other one's going to be somewhere over there, so that I've got a curve that goes like that, and of course my point of inflection is over there. So there's my rough picture. It really helps to do that first. And now I've done a pretty drawing for you. Once again, you'll see that my points are in proportion to each other. So between 0 and 3, that's going to be a shorter distance than the distance between the x-axis and negative 4, because it makes sense. In terms of drawing these curves, it can be quite difficult. So what I suggest, once again, is that you go from the different points and almost do a dot-to-dot type thing, as I'm demonstrating now. There we go. It's almost perfect. Before watching my solution to question E from the same exercise, I'd like you to try this and then come back to this recording. Start by filling in the information that you need to find, or the strategies of how you would need to find them. And this is what I mean by strategies. Fill in the shape quickly. The y-intercept you can read immediately. But write down how you're going to find the x-intercept, and quickly write down how you're going to find the stationary points. In other words, write down the first derivative and say equal to 0. Then write down how you're going to find the point of inflection. And what this does, from a mind point of view, is that it keeps your brain happy. You're going to have a whole lot of calculations going on everywhere, and sometimes that makes us confused because we've got too much going on. By reminding yourself of all the steps you need to do before you start thinking about the maths, you give yourself an opportunity to do really well in this question. The other thing I want to point out is that in every question I've written down what I'm calculating at which stage. And this is really important because markers can't read your mind. They need to know that when you've written down 0 and -2, that it is the y-intercept, that you know that it is the y-intercept. So why don't you take a moment now and solve for all of these other things. Before writing down all of the other solutions, I just wanted to take you through how to factorize this, factorize a cubic, at least when you don't have any obvious factorizing steps to do. So you'll remember that earlier on in the year you did the factor and remainder theorem, and that allows you to cheat. The way you cheat is you substitute random values in for x until you get to a point where you know what the answer, well, until you get to a point where the outcome is going to be 0. Now, one way to choose your factors is to look at that last term and look for what are the factors of -2. Of course, here they are. So let's try. I'm going to start with 1. So that means I'm doing 1 cubed minus 3. And you would do this in your calculator. And you would find out that this is going to be equal to -4, which means x equals to 1 is not a factor. So let's cross that out. Let's try x is equals to -1. And of course, you can see that this is going to work because I've already put the answer up there. And that gives us 0. So that means x can equal to -1. So our first set of brackets is going to be x plus 1. Let me just erase all of that. So that's all very well, but now it's easy to get 2 of the 3 terms in the other bracket, because this first term is going to be what times x squared will give us x cubed. And the second term, or the third term at least, is going to be what times by 1 will give me -2. This middle term is what's so exciting. And what happens in a question like this is we get confused because there's no x squared. And that interferes with the method we've used before. So that's why I've now thrown in a 0x squared. So if you've looked at some of my videos before, you'll know that I start always by writing the x and the 1 over there, and I take them from those brackets. Then I'm going to write down the other 2 terms from the other thing, but keeping in mind that I may not use those terms. In fact, let's just write them up at the top somewhere over here. So x squared and -2 come from the second brackets. Okay, now you get to choose a direction when you're going with this method. You can either choose to get an answer of 0x squared, and I got that from the second term, or you can choose to get an answer of -3x. Okay, so let's go with -3x just to see what happens. And I'm going to start by substituting x squared into here and see what happens. We get x cubed. There is no way we can add or subtract anything to go from x cubed to -3x, so I'm going to get rid of that. And I'm going to try x times -2. That, of course, gives me -2x, and that makes me a lot more happy, because to get from that to -3, I just need to get an answer of -1 when I'm multiplying 1 by something. Sorry, get an answer of -x. And the amount that I've got to multiply 1 by to get that answer is going to be -x, and that's why I have that middle term. So once we found the x-intercepts, it's time to move on to the stationary points, which I found by making the first derivative equal to 0. Then once I got to that point, I still needed to substitute the values for x back into the original function. Don't substitute them back into the first derivative. It's a real function, and that will give us the coordinates. You'll see over here that I didn't do any calculations, and the reason I didn't do them is because, once again, it's a point that's repeated. I know that when x is equals to -1, y is going to be equal to 0. Lastly, the point of inflection to look at and see that once I found it was equals to 0, x is equals to 0. I knew I'd already calculated the point, so I didn't go and recalculate everything. Before you draw a very big and fancy, beautiful representation of this function, just give it a little scribble. So I'm putting that -2 and then I'll put that as -1, and over here somewhere it's going to be 2, and I'm taking all of these from our calculations, and that's going to be somewhere over here. It's 1 and -4. I think that's all of my coordinates, and I know that it's going to be like that. Okay, remember you've got to label your axes as well. All of your coordinates must be labeled. If you are at the intercepts, you're welcome to just put the 2 over there and it's fine. Good habit is probably to do the 2 and the 0 because it is quite a significant point. And here is my neater version. You'll see that I've labeled all of my important points. Generally, all of the marks are allocated for what's happening on your graph. And so you want to fill in all of those pieces of information. If something is missing, then we may go back and look at what's happening over here and see if we can find any marks in those questions. Can't remember if I spoke about this earlier, but the reason I changed it to f of x was because I like the notation better, especially when writing down what the first derivative is and second derivative. I also like that when you're using that notation, you can show that you're substituting 1 in for x, and you don't have to write down every kind of explanation possible. It's just a faster way to work with it. So G is the last one we're going to look at, and you'll see that I've immediately put all of the answers up. I haven't withheld them. The reason I've done that is because some of the answers give quite weird results. There's like decimals and stuff like that. So as you're doing it, I don't want you to feel insecure about what's happening. More than likely, if you are asked to plot any kind of cubic function, you will have some kind of weird result somewhere. So like here's the stationary points. Okay, but to go through it, you'll see that once again, the shape is defined by the fact that A is positive. The y-intercept is what we're adding at the back. The x-intercept you can find by using factor and remainder theorem. The stationary points, you find the first derivative, you make it to 0 and you solve for x, and then you substitute those values in to the original function. Use your calculator to get the answers. Second derivative is used to find the point of inflection, and you make it equal to 0. So, sorry, I should have written here somewhere that 0 is equals to 6x minus 16. And then it would go to that. And of course, once you've found it, you then substitute that value in, and you'll get a funny value over there. I found this one quite irritating to draw because the proportions, well, they're difficult. I can't have 14.8 all the way up here. So what I've done is I've kind of stretched out the x-axis and compressed the y-axis, so it's not a 1-to-1 ratio, but I've still got all of the important points. I'm still showing what the shape is, so I'd still get good marks for this question. In fact, I would say I get full marks. Anyway, that's enough from me for now. Much love.